Mario parlo. Merci beaucoup, Fabio, pour l'invitation dans ce splendide lieu. Et merci aussi de m'avoir donné l'occasion de regarder dans la bibliothèque la correspondance de beaucoup de gens très connus et très importants pour le développement de l'architecture. Entre autres, Herwijnen. On va y revenir dans le chapitre que vous connaissez bien, Icaro. Et là-dedans, j'ai trouvé une lettre qu'il a écrite à Olga, la femme qui a fondé Eranos, dans laquelle Schön y a une première version d'une théorie de l'unification de toutes les forces qui étaient connues à l'époque. Et ça, c'était très à la mode. Einstein y a essayé aussi. Mais ni Einstein ni Schrödinger ont réussi parce que, bon, c'est bien connu, en vieillissant, la créativité disparaît un petit peu. Et donc, mais il y avait aussi des choses qu'ils ne savaient pas alors à l'époque parce que les interactions faibles des forces n'étaient pas encore connues. Donc, c'était impossible de toute façon de réussir. Mais ça m'a conforté dans l'idée que je peux toucher un petit peu à la physique. Dans mon discours, mais c'est clair que de trouver le bon niveau, c'est pas évident. Alors, je te remercie beaucoup parce que pendant les derniers 6 mois que j'ai mis à préparer cette présentation, j'ai appris énormément de choses. Il y a une littérature sur le sujet, donc la liberté qui touche à la physique, c'est énorme. J'ai essayé de faire une synthèse. Il y a beaucoup de choses que je ne comprends pas. Et j'essaye d'extraire ce qui pour moi est connu et clair. So, now I will switch to English because English is easier for me to give a more technical presentation. I will try to be clear and slow. If you have any questions, not clear, ask, interrupt. I don't mind, it's fine. If I can't answer, I will tell you, and I will go on. If I can answer, I will give you the reply. So the title of this talk is From Boltzmann's Brains to John Bell's Socks. And I hope it will be clear later on with the presentation what these things are. But you may have heard Boltzmann's brains, maybe you know a little bit about it. Maybe you've heard about John Bell. I hope that after this talk you will understand what these things are. It can be explained. So my field, as Sandro said, I work in experimental high-energy physics at CERN. I work in 3 experiments. The one on the left, is a small experiment that tries to detect neutrinos. These are small elementary particles that are very difficult to detect. We try to find them coming out of the LHC. Then there's another experiment that's been running for almost 20 years called LHCb. This is flavor physics. Flavors are the names of the quarks that are sitting inside elementary particles, inside particles, not elementary particles. And then I'm also working in another experiment called SHIP, which will do the search for dark matter. It's not yet proved, but we're doing studies, we're designing the detector, and we're writing documents and go through committees, and we hope that soon this will be proved. So this is what I do. It's a completely deterministic world, right? There's cause and effect. And science here, as far as I understand it, is the search for the causal laws that are behind the phenomena that we measure. You know, there's another very important principle that we will apply, that is, to measure is to know. If you don't measure, you don't know. So we need to quantify things so that we can measure them. Now, what does the name freedom stand for? And you see here a picture that describes it, I think, quite well. You have right, you have wrong, and you have freedom. You can choose one or the other. So what I try to do is to reconcile freedom with determinism. Because as I said, we're working in this world of the causal world of cause and effect. So how can we reconcile freedom with determinism? And this is the problem of free will, meaning I could have chosen something else. And determinism means everything that happens follows from a natural or divine law. Every event has a cause. Opposed to that, we have indeterminism. Indeterminism means events can happen without a cause. By the way, there is an Italian translation of my talk. I think you can find it, or maybe you already have it. It points out. Okay, good. So you can follow the sections in the article. Follow the sections on the presentations. Okay. So if you can read quick, then you can get the Italian translation. If my English is not clear enough for you. So we go to this picture that you've already looked at in the past hour and a half. And I cannot explain, the significance better than Jocelyn did. However, by the way, I say Peter Grote. The thing that I picked this picture because it is a beautiful illustration of a beautiful story. I think the myth of Icarus is really fantastic. And I will just retell it, you've heard it already earlier, but I'll pick out the points that I think are important for me to do with freedom and free will. So Daedalus, he was a famous architect in Athens, and he was so good that his sister had a son called Talos, and she sent Talos to learn from Daedalus, the art of the craft. And Talos, he was really brilliant, Icarus, he once he was flying, he was so, he had the feeling, the sensation of freedom gave him so much power and confidence in himself that he decided, that out of curiosity, to go and fly a bit higher than what he could. Now, nowadays, we know that if you go higher up, you actually get cold, so the wings would have stayed on. But he would have still died of asphyxiation. He wouldn't have had enough oxygen. Anyway, so Talos, the Perdrix, he put in the head of Icarus the idea to go higher. Fell in the water, died, and Perdrix was happy, because he had it that. So, as I said, I think that these stories are, just a much better explanation. But the things that I got out of it are, do not try to be like the gods or better than the gods. Right? This is hubris. But this idea had a huge influence, right? We have to. I'm talking in the context of science. So be moderate. Don't go too high. Your wings will melt. Don't go too low. But his freedom pushed him to go and do something that he was forbidden to do. Right? That is, the best thing to make a child, if you have children, to make them do what you don't want them to do, is to tell them you cannot do it. So he did it, right? And then the conclusions are, so predestination exists, because everything is predetermined by the gods, and determinism exists. Free will does not exist, right? You exercise your free will, but nature, if it's not the gods, the law of nature will punish you, because if you go too high, you will fall down. So then we have the following example of the exercise of free will. This picture actually is also by this is Jan Breugel the Elder, not the same one as the one from before, and Peter Paul Rubens. It's in the Maurits house in The Hague, but it might be a copy, but not so sure. So this is the tree of knowledge, right? And it's probably nicer if I explain to you while you can look at the picture. So what is happening here is that Satan, in the form of a snake, tells Eve that they're in the Garden of Eden. They can eat from any tree they want except for this tree, because it's the tree of wisdom. And when they eat the apples from this tree, they will know all. Remember that before they ate, they were immortal, right? God made man in his image. He was immortal. They were both immortal. So Eve, weaker sex, and that's the interpretation of the Christianity, then seduced Adam to eat the apple. And then God was very angry, so he expelled him from the Garden of Eden and made him mortal. So this is a myth, if you like, to explain why people are mortal. So they both, indeed, they were told not to do something, but they exercised their free will, and they did it. As a punishment, they become mortal. But the morality of this is that, this is an explanation of evil and mortality in a universe created by an omnipowerful and benevolent God. Right now, this is a problem. This will give a contradiction, right? If you have an omnipowerful, benevolent God, well, why is there the bad things? Why is there evil? Right? So then he cannot be omnipowerful. However, if it's his will to have evil, then he cannot be benevolent. So an omnipowerful, benevolent God, as Christianity teaches us, is logically incorrect. Also, we should not try to know everything, right? Don't eat from the tree of knowledge. Don't try to. So again, these ideas, they stopped the progress of science for many many centuries. Now, the outline of this talk will be, first of all, I will go to the determinism and the laws of the classical laws of nature. And we will see that although this is often interpreted as the death of free will, maybe it is not the case. Then we will go to statistical physics, that was physics that was developed in the 19th century to explain the movements of heat. And there, indeterminism, because of the statistical nature, is coming back. In the second part, after the break, I will go and talk about indeterminism in the new physics. So quantum uncertainty, Sandro already very clearly explained, the free will in an indeterministic world. And then in the last part, relativity of space and time, there is no absolute past, no absolute future. So, you know, the future in a sense is already there, right? And can we change it? So my tools, or the tools of scientists, are mathematics and logic. I will use mathematics, a bit like Latin. You know, in the medieval ages, people used Latin to communicate because that was the language that everybody knew. With mathematics, it's the same. It is the language that everybody knows, or, you know, Chinese mathematics, Russian mathematics, Italian mathematics, it's all the same. It's the same language. And we use it to give an unambiguous description of the models that we're trying to make to describe nature. Now, we have to be very careful here because Gödel in 1931, I don't think he actually ever came here, unfortunately, but he proved that there are in certain mathematical systems based on axioms, like the system of natural numbers, there are theorems that exist that cannot be proven. So one has to be careful when we use mathematics. Also, don't confuse the math with reality. You know, entanglement exists, but we have to be very precise in what we mean by this. You know, we should not describe it with confuse it with reality. Then, as I said, the concepts of omni and self-referencing, which in fact we also see in several lectures, right? An effect has a cause, has another effect, has a cause, and so on. You know, you can go back in an infinite sequence of causes and effects. But that also gives a problem. If you get to the cause, that is the cause of all the other effects and causes, you know, this was pointed out by Bertrand Russell in 1901. And what he said was, if you take, for example, humanity, everybody has a mother, but not humanity. Humanity does not have a mother. And you cannot, the concept of a mother of humanity doesn't exist. So, and this is mathematically, this is the paradox of the sets, of all sets, that they're not members of themselves, right? If it's a member of itself, then it has a member, so it cannot be a member of itself. If it's not a member of itself, then it's also a contradiction. So this, we have to also be careful when we discuss things that are to do with everything. And that is that's a temptation that we frequently get into. And here the omnipotent benevolent God. So, and then again, the concept of free will is a self-referencing concept. So, you know, language and logic, we have to be careful. So, determinism and the laws of nature. If we go back to the beginning of what is considered to be the birth of scientific thinking, this is Anaximander of Miletus. He lived around 550 before Christ. And he was the first one to explain natural phenomena without having to go to a god. For example, you know, the wind. The wind is not because Neptune was blowing, or Neptune was unhappy, so he blew against Odysseus' ship, but then sank. This is not so. It's because the air goes from hot to cold. That is why there's wind. And Anaximander actually, he said this, he knew this. He knew also they thought at the time that the water was the air origin of everything. So they thought the earth was floating in water. And Anaximander said, no, that's not true. The concept of up-down is not because they were floating in water. The concept of up-down is related to the earth. So if you go to the other side of the earth, up-down is still, from the heavens down to the earth. That was Anaximander who came with this idea. So, unfortunately, later Stoic physicists, they identified the laws of nature with God, and they said, well, everything God knows, it's all God's will, and everything is completely determined. Plus, trying to know more than is given to man is a sin. And this was still a very common idea at the beginning of the 16th century. As you can read in Erasmus's the praise of folly. In here, he ridicules the idea of scientists that are trying to achieve knowledge of what lies outside the universe. So Erasmus was a fascinating man, and he came into a dispute with Luther, Martin Luther King, the guy from the 96 theorems on the Church of Wittenberg, I think it was, no? So Luther, he thought that everything was totally determined. Everything that happened was God's will, even evil. It was all God's will. And Erasmus, the humanist, he disagreed with this because he said, if everything is predetermined, then how can you account people for their actions? They have to be responsible for what they do. And Erasmus, so he wrote a book on this called On Free Will. I discovered all this while I was doing it. It's amazing. And so then we come a little bit later to Spinoza. And Spinoza, he was the predecessor, actually he was the predecessor of Kant. Right? Kant got a lot of his ideas from Spinoza, but this was a little bit forgotten. I don't know exactly why. But anyway, he worked as a lens grinder for Christian Huygens. Christian Huygens was the guy who first observed the rings going around and the moons of Saturn, the rings around Saturn and the moons. So he knew a lot of science. He was involved with it. However, he wasn't too bothered about science. He didn't see the link between science and what his philosophy. So he said, free will is an illusion, but freedom can be achieved. So he claimed God is the cause of everything that exists, and God is the cause of itself. I showed you before that this is an inconsistent statement, but he didn't see that. And he influenced, so this is called the principle of sufficient reason. He influenced Leibniz, and later, and also someone else called Maupertuis, the French, you will know this. He was the guy who went to the North Pole, and he actually measured that the Earth was flattened at the poles. It's an amazing story, but the Maupertuis was the man who invented the law of least action. So that means if you have a river that starts at the top of a mountain, the river will find the path which is easiest for it to go down. That is the principle of least action. It is a key principle in physics, also in modern physics. Right? And that is all at the base of this principle of sufficient reason. Of course, Voltaire didn't like it, and he wrote Candide, maybe you know, where he ridicules Moberty and Leibniz, because that's the idea that we live in the best of all possible worlds. You know? So the idea was nothing happens outside the universal laws of nature. So, and freedom of will, free will, is an illusion that comes because of our ignorance of the cosa. So basically, classical physics is the study of matter on a human scale. This is what we call macroscopic objects, big objects. And of course, the person that we all know, Isaac Newton, was the man who first came up with Newton's laws. Some people say this was the greatest intellect of all times, or the greatest physicist of all times. But he certainly created, he was at the basis of all physics that we apply today. Because before then, it was not so easy to quantify things, but he had some mathematical laws that explained how the particles moved, how the stars moved, how the Earth moved around the sun, and so on. And then a little bit later, this was the time of the French Revolution, Pierre-Simon Laplace wrote a book called the Céleste Mécanique. And of course, this is a notoriously complicated book. Right? I'm not sure that many people at the time understood it or were able to read it. But anyway, he gave a copy of this to. It was several books actually. I think it was the second book. He gave a copy to Napoleon. Napoleon first, thank you very much. He read it, and then Laplace a bit later saw Napoleon again. And then Napoleon said it to him, well, I read your book, but in it, I saw no mention of God. And Laplace's answer was, sire, I have no need for that hypothesis. Because what he said was that if some super intelligent being knows the position of all molecules and all their speeds at a given instant, from that, everything that comes later can be calculated and predicted. So the universe is totally deterministic. Now, this had a huge influence, I just mentioned it, on the 19th century literature. Zola, Flaubert, Balzac. This gave rise to the naturalism, the stream of naturalism, where their actions are governed by inborn hereditary factors, because of course there was also Darwin that had a big influence at the time, the past experience involved, and the circumstances that we live in. And so, of course, Madame Bovary ended up tragically. Of her own doing, by the way, she was unhappy and she committed suicide. But there's also influence in other languages, including the Dutch literature that I know better than the French literature, a guy called Couperus. And this is a story about a man who goes to the theater. And he has his looking glasses to look at what's happening in the theater. But downstairs, he's sitting in the balcony. He sees a man completely bald. Fortunately, I don't see anybody who's bald. But almost, yeah. And the bald, be careful. The bald man's head is shining in the light, and he's looking, but he has to look at the bald head. Right? So, and okay, then he goes home. A few weeks later, there's another presentation, and the man is there. And he cannot, keep himself from taking his pair of binoculars and throwing it down on the man with the bald head. Because he could not do any other way. He didn't have free will. He had to do it. So, is this a death of free will? Well, not completely, because supposing that there is this supernatural being that can calculate what I'm going to do, right? I'm going to drink coffee or tea, he knows. And he says, oh, I know what you're going to do. You're going to drink coffee. Say, oh, no, I'm going to drink tea. Right? So Now, if we go a step further, I can say, okay, now supposing I could do it, supposing I knew what I was going to do, right? Then I can do it, but only I can exercise my free will to do what I predict I do, only if I follow my prediction. If I don't follow my prediction, then free will. Okay, so there is an element of free will that is still possible in a completely deterministic world, and this is nicely said by Gerard het Hoofd, the Dutch physicist, he won the Nobel Prize in 1999. So he said, even the best conceivable computer cannot compute ahead of time what I will do, simply because nature does her own calculations much faster than any man-made construction can ever do. I think this is also important in the context of ChatGPT. Right? There is no need to demand for more free will than that. So although it may be determined, since in practice you cannot calculate it anyhow, you have free will. Now, despite the fact that classical physics is completely deterministic. So then, the end of or in the 19th century came statistical mechanics. Does this mean the end of determinism? There, matter is composed when finally, scientists started to understand that matter was made out of small particles, they called molecules, that were randomly moving. And so to describe something on a macroscopic level, which means a big collection of large as these molecules together, you have to do statistics. You have to calculate what is the average speed of the molecule. And so, we don't know exactly what is happening on a microscopic scale. We cannot, because we can't look there, at least at that time. We can only calculate probabilities. And so now we go into a bit more technical details to understand how this works. So nature, so at that time in the 1850s, it was the Industrial Revolution, and people had steam engines, and they needed to know how to make these engines more efficient. So the concept of energy, which means actually it's a Greek word for saying something is at work. Energy has different forms. Energy, you cannot destroy energy. Energy is there. You can only transform it. You can transform energy to heat, light, gravitation, radiation, kinetic energy, mechanical work, nuclear energy, matter, and so on. And all energy in the universe is constant. You can change it. You can change because Einstein later, it wasn't known at the time, but he came up with the famous equation E equals mc squared, meaning energy is equivalent to matter. But as heat flows from hot to cold, less energy is available for doing work. This can only happen once. Right? You cannot go back. Heat goes from hot to cold, and that's it. And that energy that happens, that is lost. And this is then what is called entropy. So entropy is the energy that is lost for doing work. It's still there because it's heated up the molecules, right? That were cold before. But this energy is no longer available for making a steam engine roll down the road. So this point of the entropy, the quantity of energy that is no longer available for doing useful work, is so if you multiply that by you have to multiply it by the temperature to get the quantity of energy, right? And when the temperature is 0, so that's absolutely nothing, it's very cold, entropy is 0. And you can also see this by something that came later, that was introduced by Boltzmann, that entropy is also a measure of disorder. in a very ordered universe, where there are no degrees of freedom, everything doesn't move, it's all time zero, temperature zero, it's very cold, entropy is zero, it's low temperature. And entropy always increases. So heat dissipates, it increases the entropy of the surrounding. That will then later lead to what they call the heat death of the universe. So you can understand it as follows. If you look at the sun is burning, right? It has fuel. It sends heat to the earth. But at some point, the fuel of the sun will disappear because the entropy, the low entropy that the sun has before burning the fuel, has changed into a high entropy situation. And so the sun does this, but all the other stars in the universe do the same. And before the sun actually has run out of fuel, all the planets around the CERN, they will implode because the sun will shrink, and under gravitation it will all be very small, and then it will become a neutron star, and it will be a white dwarf, and then that will be the end of the sun. And the whole universe has the same fate. And this is what is called the heat death of the universe. When I tried to explain this to one of my two children, they both ended up in tears because they thought it was going to happen tomorrow. But don't be worried. I think I put it in the handout in the I think it's 10 and 56 years. We have a lot of time. The human race will not survive. So Boltzmann of the Boltzmann brains, he by the way, how long do I have for this slide?
Abbiamo solo 7 minuti più o meno.
5 minutes.
Yeah, okay. 10 minutes.
Okay, fine. Boltzmann was he was here from Vienna. He married a mathematician. He was a very, very good speaker. People were sitting in the gangway when he gave a lecture. They came from all over the place. And he was a bon vivant, they say in French. He said so. He was at the origin of describing entropy as a statistical concept. The measure of disorder of the state. That if you put sugar in your cup, it will dissolve. There will be disorder. The entropy of the cup will increase. And this is because there are many more possibilities for the sugar molecules to be spread out than to stay together in a lump. And this statistical process was calculated and formulated into a law that we will see in the next slide. So this man, he was very good at numbers. So he wrote sometime in a letter that I read that to a friend. He said, usually I'm extremely good with numbers and in particular counting. The only time when I cannot count is when I've been drinking beer. I cannot somehow count the number of glasses that I got inside. So he relates entropy to the probability W. So W, these are this is what they call a macro state. So the macro state of the sugar dissolved in a cup of water and tea has many, many, many micro states because there are, a huge amount of possibilities in which these sugar molecules can be distributed in this glass, right? As opposed to the cube, where there are much less possibilities to order the sugar molecules in the cube. So he then found this law, S equals K log W. Okay, if you don't understand it doesn't matter, but just show that there's a relationship between entity and the probability of distribution of molecules in the gas or also in the universe. The entropy of the universe continuously increases. Now, the first paradox comes this was a guy called Boltzmann, you saw it. He said, well, if we take Newton's laws, they are completely, they're completely symmetric in time. You know, if I take a billiard ball and I push the ball over the table, but then I look at the trajectory and I turn it back, the two trajectories can be described identically by Newton's laws. You know, there's no reason why that, you know, should happen, not this. So they're symmetric under time reversal. So Boltzmann said, well, you know, if we have this state of disordered molecules with a certain entropy, then there's no reason why, by statistical fluctuation, you know, why I cannot go back to this to an ordered state where I started off from. And so Boltzmann, he came out of this by saying, yes, it's true, there is a statistical possibility for this fluctuation down to a low entropy state, but it is very, very improbable. And so, if just to illustrate the concept of entropy, you know, if you throw two dice, here you see the number of macro states that are possible for. So we've got, if you throw two dice, you have a macro state where the two dice came up with number 2. That is that they both have 1, or there can be a macro state 3. But here you have 2 microstates. You have 1 plus 2 and 2 plus 1. If you look at the macrostate 4, you have 3 microstates. And then finally you go to macrostate 7. And here you see that there are 6 different ways in which you can get the number 7. And that is why when you roll 2 dice, you know, you do it often enough, you will see that number 7 comes out most. So, and if you then calculate the entropy here, you see the entropy is highest for this possibility. That is why in Catan, if you know this game, they gave the thief the number 7. And you know, you can have fun when you throw the 2 dice to see whether this is actually true or not. In English, they have a nice nursery rhyme. This is Humpty Dumpty, right? He is an egg, and Humpty Dumpty sat on a wall. Humpty Dumpty had a great fall. All the king's horses and all the king's men couldn't put Humpty together again. You know, maybe you know, but this is the second law of thermodynamics. Right? You cannot, I mean, disorder, you cannot unhappen what has happened. This is the arrow of time. So thermodynamics tells if a process can occur. It does not say whether it will occur. And if you think now again about determinism, if you have a completely deterministic state where everything is known, it means that there's only one microstate. And this, therefore, is in contradiction with the second law of dynamics. So the second law of dynamics imposes indeterminism on the world, on nature. Right, that's why I go into these details. Now, here are the Boltzmann brains, right? These are some cartoons that came out of a magazine, and you know, you see here these things that look like brains that are popping up and disappearing, and even here we see this is a man who has a Boltzmann apparently brain inside. He is a Boltzmann brain. So what are these Boltzmann brains, right? So how, let's go back to this process of the arrow of time and time symmetry. If you have a so-called open or flat universe, so this is a universe that continuously expands, right? It will spend the vast eternity of its time into a featureless state when all the stars are burned up, all the atoms and molecules are spread out into nothing. So there'll be a lot of time available. And due to fluctuations in the vacuum, quantum fluctuations, by the way, that we'll come to in the second half, then after 10 to the 10 to the 50 years, remember that the age of the universe is only 10 to the 9 years, one could potentially have a Boltzmann brain popping out of the vacuum. And this Boltzmann brain, you know, since there are so many of them, could be some brain that has all the impressions and all the thoughts of us, you know, inside it. And it's even more probable to get a brain than to get a complete human being. I mean, you could also get a complete human being, but before there are statistically complete human beings, there will be a lot of Boltzmann brains. Now, you know, when I talk about this over coffee with my colleagues, they all tell me that I'm nuts, right? So it's unverifiable, but there is a lot of literature, scientific literature, calculations on this topic. So that's why I mentioned it. Right. So now I don't know whether we have. I don't think there's enough time. So there's, yeah. Well, just maybe something. The key thing that you need to remember is that the universe, we can see it's expanding because we look at the stars, we can see from the light that they send to us, it's what they call Doppler shifted, and this is because the star is moving away. It's like the train moving away. We hear the sound. The same with the light. So the expansion of the universe feeds the generation of order, because since the universe expands, one can calculate that the available entropy is increasing all the time. So there's more and more energy available for creating order. Because the reason why we're here is because we're organized. We have less energy ourselves, but that's because we get energy from the sun. So the more energy we have, the more order we can create, and maybe we can even circumvent the heat death. So So this man, John Bercow, he was the speaker of the House of Parliament in the UK, until I think it was the year 2000. But, he had a dog called Order, so he was, he was very used to saying order. But the point is, order can happen spontaneously, right? So, and that's why, in fact, we're here. Also, so yeah, if you want to, so that is the entropy in the expanding universe, and as I said, energy drives evolution. So, okay, I think we should just stop here with a break, and then we come back to the new physics after the break. Please, if you have questions, don't hesitate to ask. I know it's dense. Thanks, Lee. This meeting saw that the evolution of the universe can be understood not completely because we don't understand why the universe is expanding or how long it will continue to expand, whether it will contract, we don't know. But the fact that it expands helps us with the laws of thermodynamics to understand how order is created and how the universe works. According to quantum mechanics, nature is unpredictable and indeterministic. And that is because there are two properties that we will discuss now. That is Heisenberg's uncertainty principle and the fact that events can occur without a well-defined cause. Particles can just appear out of the vacuum like that. So this will not be a course on quantum mechanics. If you want one, you can look at the literature here. The first one is an excellent introduction to quantum mechanics. The second one is also an interesting book that you can read without knowing quantum mechanics, but it tells you what, it debunks certain myths about quantum mechanics. So it keeps your feet on the ground should you be tempted to believe something strange. Quantum mechanics is a description of matter on the atomic scale, so the microscopic properties of matter. So, and this we need also statistics to do it, but it's more on a more fundamental level than the statistical mechanics, because we now try to look at the interaction between particles. This is the basis of solid state physics, so everything that we find in computer is based on quantum mechanics, chemistry, everything to do with chemistry, pharmaceutical industry, everything is based on quantum mechanics, thermodynamics, radiation phenomena. It's all based and explained and calculated by quantum mechanics. There is no experiment to date that is found that violates its principles. Now, it doesn't mean that it's true, but it means that this mathematical model can predict nature to an incredible precision, and in a very satisfactory way. It was developed between 1900 and 1930 and it evolved from an attempt to explain black body radiation. We'll come back to that in a moment, using classical statistical mechanics. So that was done by Planck. I don't think he was a student of Boltzmann, but he was definitely very much influenced by Boltzmann. Of course, there was Einstein, there was Bohr, De Broglie, Schrödinger, Heisenberg, Dirac. There was also Max Born. I've not put him in here. He was also a key developer, and there were many others that were also part of this development. But these are the main ones. So black body radiation, what is it? It is when you take a black box, you take a thing like that, paint it black on the outside, you let radiation from the sun or whatever fall on it, you make a little hole in it, and you look at the radiation what comes out. You can look at the temperature, and you can look at the color. And when you do that, you can make these plots here. So you can see, for example, the red, the temperature is 3000 Kelvin. At green, it's 4000, blue, 5000. And it's described by these curves that you see there. So this you can also, if you think about many things can be described by black bodies. For example, you take an iron bar that is heated in the fire, or even a piece of coal in your barbecue. Right? In the beginning, it will be red, then it will get hotter, and it will become, gray bluish, and eventually it's white. So that is what happens. That is the temperature evolution of things that heat up. And this law, this displacement is called Wien's law, and it describes the curve, this part of the curve. Now, that part of the curve was described by someone else called Ray G. And what Planck did was he combined both these laws so that he could get a mathematical formula that predicted exactly the shape of this black body radiation, but he did not understand it. He did not know how this worked. And this could be seen if you calculate the average energy. So in mathematics, we indicate that by putting a bar on top. And the average energy is calculated by this formula here. You don't need to understand it if you're not a mathematician, but this is what it is called. This is an integral. And this integral means you calculate the surface underneath this curve. Now, the energy, the average energy, because of statistical mechanics, we know what it should be. There's a number that comes out, and But if you do this integral, it becomes infinite. And physicists don't like infinity. We hate it. So Planck was really stuck. And then in an action of desperation, he went back to Boltzmann, the derivation of the second law of thermodynamics. And Boltzmann, he actually made an assumption because it made his mathematics easier, not because he had an infinity he wanted to get rid of it, just because it was simpler. That when he was looking at the energy of molecules, he made cells, and he split space up into cells. And Planck, he said, okay, I'm going to do the same. I'm going to go and take energy, and instead of having energy as a continuous observable, something that can take any value, any arbitrary value, I'll give it a discrete value only, n times some constant. And then when you do that, instead of integrating, you have to sum. And the miraculous thing that what you do then, you have an infinite sum, then the result all of a sudden becomes finite. So, I mean, for me, this is an incredible thing that you go by going from a real number system, which has infinite number of real numbers, you go to a natural number system, only 1, 2, 3, 4, 5, also infinite. Somehow the same calculation becomes finite. So I think this is something very deep, right? There are different infinities, degrees of infinity. But okay, the talk is not about that. Could be one day maybe, but Planck, he gave no physical significance to this. Right? He had this formula, E equals n of this natural number times h, which is now called Planck's constant, times the frequency of the radiation. But he, now that he had it, but he didn't understand it, and he thought it's a mathematical artifact. And it was until Einstein, he explained in 1905 the photoelectric effect, where he noticed that if you have electrons, or if you have photons hitting a material, be it electric material or whatever, that if you increase the intensity, the current coming out doesn't increase. However, if you change the color, then the current increases. And this he could explain by using Planck's quantum energy. So it was Einstein, I think, actually, who introduced the word quantum. So that was the beginning of quantum mechanics. Now, if we come to Heisenberg's uncertainty principle, what you have to know that there are observables that do not what they call commute. If you take the natural numbers, for example, you know that 1 plus 2 is the same as 2 plus 1. The order in which you put these things is irrelevant. Now, in nature, there are observables that do not commute, right? Where you have A, B, so I first do A, then do B, is not the same as first doing B and then doing A. And here you can see an example. I mean, for example, this book, if you first rotate it around this axis here, X, then the physics comes up like that. Then you rotate around Y, and the book is oriented in this direction. Now, if you first take the book and you rotate it around Y, it goes in the plane, it goes like this, it's still lying flat, and then you translate it around X, and then it comes like this. So these two operations, which are completely classical, they do not commute. And there are other, more complicated observables in physics that have the same property. For example, momentum, so the momentum is like the speed and the position. If you try to measure the speed before the position, then you do not get the same result as when you measure first the position and then the speed. These are operations that are not commutable. And that gives rise to the Heisenberg uncertainty principle. We will see it in a moment. Also, the possibility in quantum mechanics of particles creating themselves out of nothing. So we have this equation E equals mc squared. So, for example, we have two equations. We have E equals h nu, so energy is equal to the frequency of vibrating something. And on the other hand, E is equals to mc squared. So we can have a vibration that we can't see, but translated into a material particle, according to quantum mechanics. And Einstein, he didn't like it. He said, as you've all heard this, right? God does not play dice. It's not, particles do not randomly appear. Now we need to know another mathematical thing called the wave function, often denoted as psi. This is a mathematical thing that the physicists use to describe states. Now, I mean, I've been looking at this blackboard here the whole time, and it is amazing for me to think that Schrödinger one day was here and he wrote his equation with the wave function on the blackboard. Unfortunately, there's no code, there's no white, otherwise I would have written it on there as well, you know, with my signature next college. So the wave function describes the observable. So you can have a wave function of a particle that describes its speed and its position. You can have these two things, they don't commute, and the wave function describes both. Now, when you observe something, this quantum object, mathematical, it becomes something classical. You know, because you measure the speed, or you measure the position. It's something, you know, this superposition, as they call it, these states, collapses into one thing that you measure, and that is the act of observation that does it. Justin also spoke about the implication of observation. I didn't really understand it, but the interaction of the observer with the picture, you know, this is yeah, I mean that is the classical analog that you could make, right? It's the fact that you observe something means that you interact with what you're observing. Oops. Yeah. So, and of course we all know the famous story of Schrödinger's cat, right? The cat is in a box. We don't know whether it's alive or dead. We have a radioactive potion next to it. When the radioactive potion decays, and we don't know when it will be, that's what quantum mechanics says, then it will hit a hammer, it will destroy the poison, and the cat will be dead. But since we don't know, right? The cat sits in this superposition of states in the box until we look at it, and then we know whether the state was actually alive or dead. So Schrödinger concocted this thought experiment, you know, to highlight this bizarre property of superposition of states. So now, what an interpretation of this is that the thing that we're observing, right, the observable of the dead cat or the alive cat, it is forced by what we measure. Right? If we have an apparatus that can detect alive cats, then we will detect an alive cat. If we have an operation that describes a dead cat, a machine that can measure a dead cat, then we will measure the dead cat. Now, the two things, alive cat and dead cat, they commute. So this is not really a very good example, right? You cannot make two, because the one, you know, your measurement apparatus that measures the cat alive, well, you can also measure that the cat is dead. But if you have these two properties, if you have a molecule with a speed or position, then you have an apparatus that measures the speed, then you cannot know what its position is. There is an uncertainty to this. So then we come to the topic of quantum entanglement. This happens when two particles interact. Now, the concept of entanglement was also coined by Schrödinger in 1925, when he wrote about the Einstein-Podolsky-Rosen paradox. And in fact, quantum entanglement was already known at the beginning of quantum mechanics. Electrons that sit in a cloud around an atom around the nucleus, they're in a state of quantum entanglement. It was just not called quantum entanglement. Any particles that interact, they then become one state. And there's one wave function that describes the state of these two particles. And so you have to, when you look at a state of, you look at two quantum entangled particles, you have to look at the state that describes both at the same time. So it may look that when you look at one particle, you can predict what you see on the other one, but that's not the way that you should look at it. You should look at the entire system, at both, because you know that one is up and the other is down. So that is quantum entanglement. Then Einstein in 1935, you see at the top right, what happens when the press misunderstands physics, right? They say Einstein attacks quantum theory, right? It always is, paraphrased in things which are not completely exact. And so, the Spookhaft right? The Germans say it's much better than the spooky action at the distance. So, what Einstein said, he said, if I have an electron and I have an entangled electron, and I measure at one property of this electron, then I immediately know what the other one is. But what he did was he mixed up non-commuting variables. So he said, if I know the position, I know the position and I know the momentum, I know the speed. So, when I know the position here, then I must know the momentum there. It's predicted automatically. This is not true, right? So, because these variables are non-commuting. Now, what he said then was, either you have a theory where there's information that is transmitted faster than the speed of light, right? I measure here the position. So immediately I send the message to the other guy quicker than the speed of light to tell him, go and measure the momentum here, So either his own law is violated, or there are some hidden variables behind it which explain underneath, quantum mechanics that we don't understand how it works. And so these hidden variables, right, you can have an example. For example, if you take a gas, it has a temperature, it has a pressure, and the volume, but the velocities of all the individual atoms are the hidden variables. Right? You could work out the volume or the temperature if you knew all the velocities of the molecules that make it up. But since we don't, we have to look at the macroscopic. So it's like, the hidden variables are an analogy of the macroscopic variables in the microscope. We thought beneath all of quantum mechanics, there are other properties that we don't know that contain the hidden variables that explain the strange things that we see. Now, John Bell, just to come back to that moment, the realism, what Einstein also said was, he said, the moon exists whether we look at it or not, right? Daedalus is there whether he's on the picture or not. I mean, we know he's there. So this is what they call realism. And this motivates determinism. A realistic world is deterministic. And so a deterministic theory has hidden variables. There must be something else that says, okay, there's something behind which causes the moon to exist, even if we don't look at it. And John Bell, starting from these assumptions of that the speed of light is never, you will never find communication faster than the speed of light. And the fact that the theory is realistic, so there are some hidden variables, he made some equations. And these equations we can see with Bell's socks. So Bell had a colleague, a mathematician colleague called Bertelsmann. And you can mathematicians have a very special, and physicists also have a dress code. And it's well known that the physicists are the worst dressed males that exist. And unfortunately, my wife takes care of what I wear, so I cannot show you my insulated socks. Right? But this guy, he probably didn't have my wife, or maybe his wife was a mathematician. And he wore old socks, right? Yellow and red. So John Bell, when he saw in the morning, he saw one red sock, said, "Oh, I know, the other sock is yellow." Because the socks were entangled, right? And so you can do a little calculation. If you call the act of measuring red A0 and you measuring red B0, and I measure yellow A1 and you measure yellow B1, then the values of these measurements are always plus or minus 1, right? I measure it, or I measure red, or I don't measure red. And then if you make this sum of these measurements together, then you will see that you can rearrange the terms together, and you have, when A0 is 1, then A1 will be the opposite, and vice versa. So then you will have here one of these terms that disappear, and the result is that this inequality is always less than 2. That is in the classical case, right? Because of course these in this case, this is there's no quantum. The socks are not quantum entangled. This is because these measurements actually commute. It's not a non-commuting measurement. So this is completely deterministic, right? The classical system predicts, and if there are no with hidden variables, right? That this must be less than 2. Now, in 2022, so last year, the Nobel Prize in Physics was given to 3 physicists, Alain Aspect and John Clauser and Anton Zeiliger. And these people, they measured this effect on quantum particles. They looked at entangled photons, and what they discovered was that if you calculate these probabilities, because you can measure it, and you can make a system that looks at these quantum particles, and you can measure what they call the spin, and then you get something that approximates to 2.8. And that is because this wave function, it is a complex, what they call in mathematics a complex object. That means it has a part that is a real number, and there's a complex number, which is, you take the square of I, it becomes -1, right? It's a bit bizarre because the square of numbers are always positive, but this is the complex number. And there, these complex numbers are what we call a phase. This is an angle. And the phase appears when you have a quantum object, when you replace this by wave functions, where you work out the probability of the wave function by squaring it. This angle appears, and then you see that it becomes 2.8 and not 2. So this was measured, and therefore we know that quantum mechanics is, if we believe that there is no faster than light transmission of information, it is not compatible with the theory with hidden variables, where there is information that we didn't know in quantum mechanics. So now from this, there have been some implications on the question of free will, right? It seems that quantum mechanics is correct. So there's indeterminism, which is part of quantum mechanics. And so we don't know beforehand what the result of a measurement will be. Right? We cannot know it. There is an intrinsic indeterminacy in the measurement. And so then there's a big leap of faith to human free will, which says, well, you know, if the result is random, anything is possible. And so there is free will. Now, randomness is not completely the same as free will, right? But okay, that is and even stronger. The two mathematicians, Conway and Cohen, in 2006, they came up with something called the free will theorem. And this also, I think, is very misleading. Because the way that they define free will is as follows. They say there's a certain number of axioms that they take, like no speed of light communication, no hidden variables, nothing is influenced by what happened in the past. Then, in that case, they prove mathematically that elementary particles also have a free choice of what they do. And now, to give a mind to an elementary particle, of course, this is not, I don't think it was what they meant, but a journalist that sees this is what we would think. So this is a very misleading way of saying it, but okay, it's a mathematical theory, they proved it, and the problem comes with, this choice as a function of the past. But Hooft, he says, if you make a decision now, you have to also modify the past. You cannot, influence, you cannot change the present without changing the past. And the example he gives is, if you look at the planets that are going around the CERN, we take the sun, we take one of these planets out, we take Mercury out, we put it somewhere else, then all the trajectories of the other planets also change. But not only now, they also have to change what their trajectories were in the past. You cannot change the present without changing the past. So, at Hooft, a big argument with these guys. I mean, who knows? I mean, it's, So then there's the idea of superdeterminant, right? And this Bell suggested that there's a loophole. So what he says is you have the Big Bang here, the beginning of the universe, and there are some instructions that are sent out to some supernova. Two of them. One in the neighborhood of Bob and the other one in the neighborhood of Alice. And the supernova tells Bob that he should measure property alpha. And then, on the other hand, this supernova here tells Alice that she should be measuring beta. So she can change her apparatus to measure this non-commuting beta. So you're back at determinism. Everything is determined from the Big Bang, depending on the initial conditions that were set at the Big Bang. So it's a little bit like Laplace. So at Hooft, he does this in a super deterministic, just to show you that there are people thinking about it and doing calculations. He uses the cellular automaton, which was actually invented by one of the guys who invented the free will theorem, Conway. So this is also, I think, an interesting example of showing how order can appear in very simple configurations, using simple laws. So this here is a lecture theatre where there's one row only. And this guy is wearing a hat. And the next day, there's instructions, everybody who sits next to someone who's wearing a hat also wears a hat. So you see, the next day, there are two people. And then after that,
the two people sitting next to these two, they're wearing a hat. And so gradually you have this ordered structure. And he showed that these ordered structures, they come alive, they do things that you weren't expecting. So this is an interesting model from which one can one can obtain order. And het hoofd, what he did was he takes this and he uses some mathematics, and he can include mathematics inside these cellular automaton without having these indeterminacy and uncertainty relations. Now, finally, the last topic, I hope I still have time. Yes. 10 minutes. Oh, 10 minutes. Yeah, I know what you're thinking. Boy, he's going to continue for another 10 minutes. Yeah. Okay, I'll try to be a little fast. Anyway, the next topic, so we saw that quantum mechanics is indeterminate. It was confirmed by the experiments that won the Nobel Prize last year. So we believe that quantum mechanics is a good way to do calculations that refer to the microscopic world. Now we go to relativity. So relativity, if you look at this diagram over here, right, this is time, and this here is space. So we have three people, and what the person in the middle does is he has a torch, and he sends light, and you see here the path of the light as a function of time, towards observer A, right? So at time, at this time here, this line moves up, and he does at the same time, he sends a signal to observer C. So you see that these signals, they appear for observers A and C at the same time. Now, if you have the situation where these three people, they're all moving at the same speed towards each other, then what happens is that B will send a signal to A that will cross, these lines, they will then rotate, and it will appear here, and the same signal will appear at observer C at this time. And in the situation, in the independent, what they call the laboratory reference frame, these two times are not the same. So although we start out with sending a signal that appears in these observers at the same time, if we move with respect to other different times, then they don't arrive at the same time as seen by this observer in the laboratory frame. And that is, of course, what we see when we're looking at the stars, right? We see the light that comes to us, but this light came to us from many years ago. And when we're looking at it, their time has advanced, and the future, in fact, has already happened for them. So we can, with special relativity, we can not say that there is an absolute past or an absolute future. It does not exist. The future is relative to the observer. My future is not the same. Okay, well, this all only happens when we're going towards the speed of light. So for you and I think we can safely say in 5 minutes we'll have lunch. But, for the people on the star, they've already had their lunch a long time ago. So there are people that say there is no free will. It's an illusion because the future has already happened. We can only wait for it to happen. We can, it's not something that we can predict. Of course, I'm not going to go and cross the road without looking. Right? So then, finally, what do we know? Right, there's this guy, Donald Rumsfeld. Right?
That something hasn't happened are always interesting to me, because As we know, there are known knowns. There are things we know. We also know there are known unknowns. That is to say, we know there's some things we do not know. But there are also unknown unknowns. The ones we don't know, we don't know.
So this was, he said this when he was being interviewed about the first Iraq war. So this I think pertained to the possession of nuclear weapons by Saddam Hussein. Anyway, so in this table here, I put a summary of the things that I think that we know, right? Classical mechanics, the universe is deterministic, chaos creates indeterminacy. So there is some degree of free will. Second law of thermodynamics, what has happened cannot unhappen. Statistically strange things are possible, right? The universe is undeterministic. Special relativity, the universe is deterministic. There's no absolute past, present, and future. Free will is an illusion. Quantum mechanics, there's an uncertainty about the outcome of measurements. The universe is indeterministic. Quantum entanglement, Bell's inequalities are violated. So this is a confirmation of the uncertainty decreed by quantum mechanics. Unknown, classical mechanics, they say free will is an illusion. Maybe it's true. It's incompatible with this, but second law of thermodynamics, the energy non-conservation in an expanding universe, it's unknown. Some people think it's true, others don't. The heat death of the universe, it's unknown. You will read a lot of popular literature claiming that this is known. It is not known. We don't know whether this is true. Boltzmann brains, very unlikely, but we don't know. Quantum mechanics, the uncertainty claim, it can be extrapolated to free will. We don't know. I mean, I don't know what you got out of this lecture, right? But that's by the side. Myself, the only thing I know after having learned all this and having read many books is that I know nothing, I'm afraid. I also don't know how many more books I should know before I think I start to understand it. The unknown unknowns, well, unfortunately, Donald is dead, so we can't ask him. So then, finally, I have some other examples of more contemporary misfortunes. And there's a very nice book where you can read all these things. And this is exactly, modern versions of the contemporary Icarus disasters. Newton poked sticks in his eye, to understand more about optics. And he had to sit in a darkened room for 3 days before his eyesight came back. And Benjamin Franklin, he electrocuted himself during a dinner party because he was trying to explain to people what electricity was. Now this guy, James Gleicher, he was the first meteorologist person, and he went up in a balloon like Icarus. And unfortunately, they had a problem when they went up because they had the hydrogen in their balloon, which was kept in by a valve, and he went up much faster than what he thought. So they were up at 11,000 meters, and they couldn't close the valve. They were going up. So his pilot, a guy called Cox, he climbed up. Of course, Gleicher, he was already passed out. He couldn't do anything. And he closed it, and then they went down. And the only thing that they were annoyed about was that the place where they fell down was 7 miles away from the place where they went up, right? Of course, they did all sorts of experiments, like they threw pigeons out of their cabin, and of course, you throw a pigeon out of the window of an airplane at 11,000 meters, it goes down like a block of ice, no? But this guy, they went up after passing out. He still went up 40 times. However, he did do science, so moral of that story is that by doing something stupid, you could actually advance science. And, so maybe there's another story of free will that you might want to exercise, although the gods forbid you from doing it. So I want to conclude with Gell-Mann, right? He's another famous physicist. So he says that
if you add the thermal fluctuation from the statistical classical mechanics to the quantum fluctuations, you could see that this contributes to a subjective impression of free will. But he says human beings probably act on hidden motives more often than they use the results of an internal random or pseudo-random number generator. This he does in the context of, neuro science, where he looks at the states of the brain and he tries to understand what's happening with the neurons in the brain. And he concludes, and I think I only can concur with that the whole matter is poorly understood for the time being. We can only speculate. So that's all.